to start the screen recording. So yes, I was telling that we basically have few kind of counters to which basically we don't give any of the data inputs. So one such counter or one such register we have, basically this you can say this is not register, because register it usually stores data. This is actually a kind of a counter. It is known as your ring counter. Okay, ring counter. So previously we had seen that this was our register, a 4-bit register. Now how do I convert it to ring counter? Simply by feedbacking this D3 to the output of this last flip-flop. Okay. So now if you see, basically if you have to write the next state equation, because these are what? Synchronous counter. So Q3 plus is equal to D3, which is equal to Q0. Q2 plus is equal to D2, which is equal to Q3. Q1 plus is equal to D1, which is equal to Q2, and Q0 plus is equal to D0, which is equal to Q1. Okay, you can see it from here. Now I am assuming that the order over here means the order of the variables or the output I am taking, it is Q3, Q2, Q1, Q0. And you can see I have one active low preset over here. Okay, active low preset. Okay, so now this active low preset, it will be activated when it encounters what? It encounters your negative edge or a negative level, you can say. Okay, so whenever suppose during triggering I get one of the signal for preset like this, so what will happen? Immediately this Q3 will set to 1. Okay, this Q3 will set to 1. So if suppose initially clock pulse, so if initially clock pulse at clock pulse 0, all the flip-flops are 0. Now if suppose at the first clock pulse, what is happening? This pre-bar is getting 0 input over here. So pre-bar gets activated when it gets 0. So it is getting at the first clock pulse. What will happen? Q3 will immediately become 1 and remaining all the flip-flop will be 0. Now after this first clock pulse, after this application, it is again going back to 1. You can see this is 1. So pre-bar is again deactivated. So it was activated only momentarily for first clock pulse. Now what will happen in the second clock pulse? If you look over here, so this Q0 basically it is feedback to this Q3. So this will come over here 0, and this one it will move over here. So this will become 1. This 0 will come over here, and this 0 will come over here. Now once again this 0 will be feedbacked in the third clock pulse. So this will become 0. This 0 will shift over here. This 1 will shift to this 0. This 1 will shift over here, and this 0 will shift over here. Okay. So at the fourth clock pulse, this will become 0, 0, 0, 1. Again at the fifth clock pulse, this will become 1, 0, 0, 0. So you can see what I am getting repeated state. So we started from 0, 0, 0. So 0 was your unused state. After that we went to, this is your 8. Okay, 8. Next we went to 4. Then to 2, then to 1, and once again back to 8. Okay, once again we went back to 8. So now this is known as your ring counter, or this is basically mod 4 ring counter. Okay, This is your mod 4 ring counter. So very quickly note it down, and then we will move on to the next thing. So note it down very quickly.
So,
Hello. Yes, tell me.
I didn't get why you are shifting one.
Because it is shift register. This is shift register. You haven't attended the yesterday's session, Shubham.
No, sir, I was traveling. Actually.
So that is why you are not able to understand. In the last
Yes, sir.
session, I have actually explained what is happening over here. Okay.
So I have to attend 3 lectures still.
Yeah. So basically, this is shift register. You can see from the next state equation also. Next state
Yes.
equation also you can see. So these are all the present state. At the first clock pulse, this will be your present state. But for here, you can see what? That this pre-bar is getting activated for the first time for momentary instance. Okay. So this is becoming 1, and remaining the initial or the present state was what? It was 0. You can see what happened over here. So look over here. So I should have drawn one more, means if it is not understood, you guys have not understood, then I should have drawn one more over here. Okay. So let me do one more thing. So look, this is clock pulse. Over here I am going to write the present state. Here I am going to write the next state. So present state is Q3, Q2, Q1, Q0, and next state is Q3 plus, Q2 plus, Q1 plus, and Q0 plus. So look, at clock pulse 0, your present state is 0, 0, 0, and at the end, means sorry, you could have even written over here first clock pulse, because now at the end of first clock pulse, initially the states were 0, 0, 0. Next state will be what? Because over here I have this preset activated, so this will become 1 for the first time. And Q2 plus, you can see it is equal to Q3, so Q3 is 0. Q1 plus, it is equal to Q2, so even this will be 0. And Q0 plus is equal to Q1, so present state, all of them are 0. So in the next clock pulse, this will become your present state, and next state will be what? So Q3 plus. Now once again in the second clock pulse, this preset bar, its input is what? It is 1. So we know preset bar gets activated when it is 1. So over here, sorry, preset bar gets activated when it is 0. Okay. So again it has went to 1. So that means we have deactivated the pre bar. So what will happen to the next state? Basically, you can see Q3 plus is equal to D3, which is equal to Q0. So Q0 is equal to 0. So the next state will be 0. Q2 plus is equal to Q3. So in the present state, Q3 was 1. This was 0. Similarly, in the third clock pulse, this present state will be 0, 1, 0, 0. Next state will be what? 0, 0, 1, 0. In the fourth clock pulse, this will be 0, 0, 1, 0. And this will become 0, 0, 0, 1. And once again, in the fifth clock pulse, this will be, sorry, present state will be 0, 0, 0, 1, and next state will be 1, 0, 0. Okay, so this is what? This is your, basically, your ring counter. Tell me if you have understood this or not. Have you understood this? So this is what? This is, you can see over here we have 1, 2, 3, 4. So this is mod 4 ring counter. Okay, so Shubham, now have you understood?
Yes, sir.
So if suppose we have a n bit ring counter, n bit ring counter, okay, so then how many will be your u state? So over here we had a 4-bit ring counter, so the u states were 4. So for n bit ring counter, the number of u states are going to be n, and the number of unused state. So from n bit counter, we can have 2 to the power n counts minus n. So these are your unused states. Okay, unused state. Okay. So now if suppose, okay, what I am telling you, that if we had started from, let me assume, for the same kind of counter, okay, for the same counter, so let me even copy this. If suppose this time we don't have this pre-input. See, pre-input I actually used because I had assumed initially all the counters were 0, 0, 0. Initially they were resetted. So I wanted one of the counter to actually have a high state. Okay. So now what I am telling, that initially we don't need to, means, think about from where did we get the initial value. If suppose the counter was loaded with this value, okay, this is what, this is 3. So what will be the next state? So now I am writing it in shortcut. I am telling that initially your counter was loaded with 3. Now we don't have to worry from where this 3 came. Okay, just assume, or you can even say that pre-bar for this and pre-bar for this were activated. Okay, this were activated, so that is why q3, q2, q1, q0 initially at clock pulse 0, it is 0, 0, 1. After, immediately after this clock pulse, okay, after the first clock pulse, it was removed. So that means in your first clock pulse, basically this will transfer over here. So this will become 1. This 0 will be shifted over here. This 0 will be shifted over here, and this 1 will come over here. In the second clock pulse, this 1 will be feedbacked over here. So 1, 1, 0, 0. In the third clock pulse, this will become 0, 1, 1, 0. In the fourth clock pulse, this will become 0, 0, 1, 1. So once again, you can see I am returning back to the same state. So from 3, I went to 9, then 12, okay, then to 6, and once again back to 3. Okay, so this is also a mod 4 ring counter where I have initialized the state from 3. Okay, I have initialized the state from 3. So always you cannot get more than 4 states over here. You take any initial value. If suppose you start from 0, 1, 0, okay, start from 0, 1, 0. So this is your 0th clock pulse. So after the next state, this will become 1, 0, 1, 0. At the second clock pulse, this will become 0, 1, 0, 1. So you can see there are only 2 states over here. Okay, so the maximum for an n bit, maximum counting state for n bit, it will be mod n. Okay, or else you will have less than n u state. So are you getting the point what I am trying to say? Are you getting the point? If suppose, if you think, let us start from 7. Okay, so initialize the counter from 7. So this I had initialized from 5. So now if suppose you are thinking, let us take any other random value. So initialize the counter from 7. So 7 will be 0, 1, 1, 1. So in the next clock pulse, this will become 1011. Okay. In the second clock pulse, this will become 1101. In the third clock pulse, this will become 1110. In the fourth clock pulse, this will become 0111. So over here, this is 7. This is what? 9 and 2, 11. This is 13. This is 14. And once again, we are back to 7. So you can see this is also mod 4. So you can start the counter, you can initialize the counter from any state, but you will never get more than mod 4 in a 4-bit ring counter. Is this concept clear? Is this concept clear to you guys? So note it down very quickly, whatever I have said. Noted? So the next we have is what? Johnson counter or twisted ring counter. So in twisted ring counter, basically what we do, we have over here, see in the last case in your normal ring counter, we were taking the feedback from here. Okay, we had taken the feedback from the normal output. But in your twisted ring counter, we are going to take the feedback from here. Okay, from the last complemented output. So now if that is the case, this is also known as twisted ring counter or Johnson counter. So now if you want to start, see basically here even we don't require pre-bar or pre to initialize. We can simply start from 0, 0, 0, 0. So if suppose at clock pulse 0, initially all the flip-flop are resetted. Okay, so 0, 0, 0. At the first clock pulse, you can see this Q3 will be what? Basically, you have one inverter over here. Okay, whatever is the Q0 state, that will be inverted. So this will become 1, 0, 0, 0. Now I am not writing the next state equation. Okay, next state equation, you can write it yourself. I am not writing the next state equation. So you can see at the first clock pulse, this becomes 1, 0, 0. In the second clock pulse, once again, this has to be inverted. So this and this bit will be shifted. So this will become 1 because there is an inverter over here, and this one will be shifted over here, and this 0 is shifted over here, and this 0 over here. In the third clock pulse, once again this will become 1, 1, 0. In the fourth clock pulse, this 0 will be inverted and shifted to Q3, and all the remaining ones will be shifted one place. So now look at the fifth clock pulse. This one will be inverted, so this becomes 0, 1, 1. In the sixth clock pulse, this will become 0, 0, 1, 1. In the seventh clock pulse, this becomes 0, 0, 0, 1. And in the eighth clock pulse, this becomes 0, 0, 0, 0. So we started from 0, then we went to 8, then to 12, then to 14, then 15, then 7, and then 3, then to 1, and from 1 again back to 0. So this is how many states we have. So 1, 2, 3, 4, 5, 6, 7, 8. So this is mod 8 twisted ring, or you can say Johnson counter. Okay, so this is mod 8 Johnson counter. So over here, the number of U state is equal to how many? It is equal to 8. Unused state will be how many? So total states that we could have generated using a 4-bit counter, that is 2 to the power 4 or 16. So 16 minus 8, that comes out to be 8. Okay. Now if we want to write it in n bit, can you tell me for n bit what will be the number of U state? For U state means for n bit, what will be the number of U state? 2n. Very good. So this will be 2n, and unused states will be 2 to the power n minus 2n. Okay, 2 to the power n minus 2n. Okay. So let me ask you, if suppose we initialize this twisted ring counter, okay, if we initialize it from 2, then write the subsequent stages or the subsequent count very quickly. Do it yourself. So what will be the subsequent count states? Very quickly write. I should have brought some questions of ring counter, but that's okay. So today we will finish the theory part, and in Sunday's class we will see questions of this chapter. See, basically over here, when I have told you that this is twisted ring counter, that means Q3 will be what? It will be, there will be an inverter over here. So at first clock pulse, this 0 will become 1, and remaining all the bits, it will shift by one place. So 0, 0, 1. At the second clock pulse, this 1 will become 0, and all the remaining bits are going to shift by one place. In the third clock pulse, this 0 will become 1. Remaining all the bits are going to shift one place. At fourth clock pulse, this 0 will again become 1, and this will, all the bits are going to shift one by one. In the fifth clock pulse, this will become 0, and this will be like this. Sixth clock pulse, this will be 0, sorry, 1, 0, 1, 1. Okay. In the seventh clock pulse, this will become 0, 1, 0, 1. Okay. So any repeated states that we have? So seventh we are getting over here. Okay. So any place, any repeated? Okay, fine. So at 8 clock pulse, what will happen? This will become 0, and this will be 0, 1, 0. Yes, now it is getting repeated. So we had started from 2, we are again returning back to 2. So we started from 2, then we went to 9, then to 4, then this is what? This is 10, then 11. My 10 is looking like 0. Then to 11, okay, this is 11, then 6, okay, sorry, this is 13 na? So that is what I was thinking, what happened over here. So this is 13, then to 6, then to 11, then to 5, and from 5 again to, so 1, 2, 3, 4, 5, 6, 7, 8. You cannot have more than 8 states over here, 8 U state in a 4-bit Johnson counter. Okay. So you initialize with any value. It is up to you. You can initialize it with any value, but still you will be getting what? You will be getting just maximum of 8 U state. Okay. So, okay then. Now we have few questions. Very good questions I have taken. So first solve this question. What can you understand from this question? And before this means digital electronics, it gets over. I am means solving all the questions of this computer science. So I will be actually taking one session where we will be discussing the questions of computer science. Okay. So solve this question. This is one very good question. How many of you are from EC? So Shruti, she is from EC. All of you guys are from computer science. So this is actually a question of finite state machine. Okay, so it is also written over here, finite state machine. Basically, what do you understand by the question? See, you have read the question. Just tell me, what are you understanding from the question? What are you understanding? At least let me know that. Okay, so let me do that. So the state transition diagram for a finite state machine with state A, B, C and binary input X, Y, Z is shown in the figure. So this is one FSM state diagram, and X, Y, Z are basically the inputs. Now you have to tell me that out of A, B, C, which transition is defined ambiguously for the input. Okay, so for A, if your transition to B or C, if it is defined ambiguously means what? Confusing way, that there is no finite way or a finite rule, okay, for which your state is transitioning. So ambiguous means what? Confused state. So from A to B, if it is confused, you are going to write A. Transition from state A are ambiguously defined. If your transition from B is ambiguously, from B to A or B to C, if it is ambiguously defined, then you are going to write what? Option B. If from C, any one of the state, that whether you go to A or go to B, it is ambiguously defined, then you are going to write option C. If for all the three, the states are ambiguously defined, the transitions are ambiguously defined, you are going to write option D. Now, how are you going to make the truth table? So, truth table, how are you going to make? So, have we understood the question? Tell me first. Have we understood the question? See what I do. So first I am checking for option A. So option A states that transition from A are ambiguously defined. Okay. So option A states that your A is ambiguously defined. So I will write over here that state A, I am checking for the transition of state A. So basically the combinations of X, Y, Z I will be having. So they are from, so these will be your next state. Next state. So X from 0, 0, 0 till 7 we will have. Okay. So now look, my present state in each of the case is A. So if I give X equal to 0, Y equal to 0, Z equal to 0. Now hopefully this diagram is clear to you guys. Look over here. So is this visible to you guys? So I will zoom in a little bit over here. Okay. So look, my present state in all the cases it is A. So when X0, Y0, Z0, you can see I am going to B. Fine. Any other place that I am going over here, look. So for X0, Y0, any other option that is available? So here no. For Y equal to 1, we are staying at A. Or over here X0, Z1. And over here you can see from A to C we can go only when X equal to 1, Y equal to 0. Okay, fine. So now look, when X0, Y0 and Z1. So where are we going to transition? So X0, Y0, Z1. So X0, there is nothing specified about Y over here. Okay. And Z1, any other place you can see. So this is one transition from A to B. This is from transition from A to A. Okay. And this is transition from A to C. And there is one more transition from A to A. That is from when X is 0, Z is 1. Okay. So over here you can see out of this 3, only this condition is being satisfied because X is 0 and Z 1. So I will be staying at A only. Next look, X0, Y1, Z0. So whenever Y is 1, you have to stay at A only, because you can look over here. It is defined clearly. In any other 4 places, here Y 0, here Y is not mentioned, and here Y is 0. So whenever Y is equal to 1, you have to stay at A only. Now next look, when X0, Y1, Z1, okay. So Y1, Z1. So first search where is Y1 over here and Z is 1. So here Z is 0, here Z has not been mentioned, and here Z is 1, but Y is not mentioned, and here Y is 1. So even if here it is not mentioned, but because we have Z1 over here, so I will take this case, or you can take this case also. Okay, but still you are going to stay at A. So Shubham is telling option C. We will see. So this is A. Now look, X1, Y0, Z0. So X1, Y0 we have only at this case. In all the other cases, there is no X1. So you are going to see. Over here also you will be going to see X1, Y1. So where is X1, Y1? So here we have X1, Y0. So this will not be the case. Here we have X0. So X1, Y1, you can see I will be taking this case. Why? Because there is nothing mentioned about X, but Y is mentioned to be 1. So this will be A and this will be A. So you can see for all the different combination, the next state is perfectly defined over here. Okay. Next state is perfectly defined over here. Now, whenever there is one trick I will tell you. In such kind of question, whenever we check the option, so what you should do, you should check the first option, then check the last option, then this option, then again this option. Okay. So that actually reduces the chance. Why? Because sometimes the person who is setting the paper, they usually give the last option as your answer. Okay. Last option as your answer. So then what happens if students, they start checking from the first option, then it will waste your time. So it is better that you alternately check the first and last continuously. So here you can see the option D is what? All of the state transitions are defined unambiguously. So that will happen if you check for any, that will not happen. Why? Because all of the state transition are defined unambiguously. You can see A has been defined properly. Okay. A has, okay, so here it is said unambiguously. So you will make this conclusion only after checking for state A, state B, state C. So you can see it is given unambiguously, not ambiguously. So now let us check for state C. So I am telling you what? Constantly do what? Alternate between the first and last. So last over here is option C. So let us check option C over here. So I won't be having space over here. So it is better. So now let us check option C. So state is C now. My present state is always C. So X, Y, Z. And next state is going to be, we have to find out from the combination of X, Y, Z. So this is 0, 0, 0. Okay. So now check. So I will be erasing this now. So look, our present state is C. So for C, what are the state transition? This is one of the state transition. Another you can see is this one. Okay, so I will zoom in the diagram a little bit. So this is one more place. Okay, you can see over here. At this place we are having one more transition, and over here also we have one more transition from C to other state. Any other place that we have? No. So now look over here. When it is 0 0 0, okay, x0 y0 z0, so you can see only place that is available. So here you can see z is 0, y is 0, okay, and x0 we don't have any place. So here y is 0, here z is 1, but, and here y is 0 but x is 1. So I will take into consideration this place. So this will go to C, because we don't know anything about xy, so it can be 0 0. So we will take it C. Now look, z is 1. So z is 1 only at this place. In no other place you have z equal to 1. So you are going to, okay, sorry, I am very sorry. So I might have not seen. So this is the case for this transition. This is from B to C. I'm very sorry. This is for this one, and for this one we have x1 y1. Okay, so for xyz equal to 0, here y1 z1, x1 z1, and here z0. So obviously this is going to be C. Now look, x0 y0 z1. So here z is equal to 0, so this transition will not take place. Here you can see z is equal to 1 and z is equal to 1, but x is not equal to 0 and y is not equal to 0. So that means what? I don't know for 0 0 1 what will be the transition. You can see I don't know, because here z is equal to 1. Okay, z is equal to 1, but x is equal to 1 and y equal to 1, and here z is equal to 0. So I cannot make a comment what will happen when I reach this state, because in this cases you can see x0, so this cannot be the case, and here y0, so this also cannot be the case. So this is unambiguously defined. We actually don't know what will be the state when our present state is C and your input is 0 0 1. We don't know what will be the next state according to the state diagram given. So did we understand this? Tell me yes or no. Did we understand this or not? Shubham has already given the answer. Raju, what about you? Piyush? Piyush, did you understand? So now you can see, you can directly mark option C as your answer, because you can see for one of the input condition, our next state, we don't know what will happen. So no need for checking. But still, if we are solving, so it's okay. We can see. So here you can see x0, y1, z0. So again, you can see over here, y is 1, okay, but z0. So z0 we have at this place. We don't know what about 1. So I can comment that this will be C. It's okay. I can take this to be C. Here you can see what? Again, y1, z1. So any place that we have, you can see it is specifically defined over here, y1, z1. So this will go to B. Look over here, x1, y0. So x1, y0, we have over here x1, but z is 0 over here. So this cannot be the case. X0, y, sorry, at this place. So x1, y0. So over here also we don't have x1, y0. Okay, so this can be the case, because here x equal to 1, z equal to 1. So there is no constraint on y. So I can assume it to be either going to A, okay, either going to A, and also you can see over here that z is equal to 0. So here z is equal to 0 and x and y are basically don't care. So I can take this state also. So this can remain at C also. So you can see this state has also been ambiguously defined, because when we have this input combination, the state, it can either go to A or it can go to C. So present state, it can transition into only one next state. It cannot transition to two states. So whenever we have drawn your diagram, like state diagram from 0 to 1, 1 to 2, okay, Now we haven't drawn a state diagram like this from 2 to 3 and 2 to 5. So we haven't drawn a state diagram like this. So this is ambiguous. From 2 it will either go to 3 or to 5. It cannot go to both. But here you can see for this particular input combination, it is going to C as well as it can go to A also. So that is why your C is ambiguously defined. So we are not going to check this anymore. Directly you can mark option C as your answer and you can move further. Okay. So homework will be, you have to find out for B. Okay. Option B, you have to check and see that it is unambiguously defined or not. Okay. So option B, you need to check yourself. So the next question is this. Very quickly tell me what will be the answer. Sir, module number. What module number? Array, mod number, that is. Mod. What will be the mod? Mod means module. So first tell me if this is what? Up counter or down counter? Very quickly. Up, down. Which one? So your answer should have been given in like 1 second. We are using clear. So that means it is up counter. Still you guys are not revising. Okay. I am very sure. You guys are not revising. See, if you don't practice, you will feel all this thing very tough. Okay. It will be very, very tough for you guys. This is up counter. Okay. This is up counter. Okay. If this is up counter, now there are two ways to identify whether this is up or down. You can see clear bar has been used over here. So I have told you that we use clear or clear bar in case of up counter. Okay, up counter only. So either you can determine it like this, or you can see over here the clock edges are negative edge triggered and it is taken from your positive output of all the positive terminal, means the non-complemented output. So different sign means up counter. So this two way you can determine. Next you have to see what, basically if it is up counting, so let us write, you can see over here it has been given the output is A. So even in examination you don't need to do all this. Okay, so you can see directly over here. So I will even share the trick, but first let me solve it in long way. So this is A. So you can see this is active low clear. Okay, this is active low clear. So up counting will take place like this. Okay, anything mentioned over here, whether it is synchronous clear or asynchronous? Asynchronous or synchronous? If it is not mentioned, then what we will take? Asynchronous. Very good. If nothing is mentioned, I have told that we are always going to take what? Asynchronous. 0 1. Okay, so I have messed up over here.
So,
Yes, tell me.
so the bubble with clock is already showing it's asynchronous, right?
With what bubble with clock?
Clock pulse, so it's already showing that so that it's asynchronous counter.
Which one? I am
In the
asking
diagram.
not about asynchronous counter. I am asking whether this clear is synchronous or asynchronous.
Okay.
So you haven't watched that lecture or what?
Didn't watch that lecture, so
So you need to watch. So
yes.
this A is actually the output of this NAND gate. And we have already seen that with clear bar, we use NAND gate. Okay, with clear bar, we use NAND. With clear, we use AND gate. Okay, so with clear bar, we use NAND, and with clear, we use AND. I have given all the tricks for this. So now you can see this A is basically what? Q2, and another input is Q0. Okay, so this A means the clear will be activated when we get 0. So here you can see Q0, sorry, Q2, Q1. So this will be 1. Okay, this will be also 1, 1, 1. Okay, over here you can see this will be what? This will be 1 into 0. So this will be also 1. For the first time you will be getting 1 over here. So this is 0. Now as this is your asynchronous clear, so this state is not going to be counted. Only this 1 2 3 4 5, these 5 states are going to be counted. So this is mod 5 up counter. Now if we had to solve in examination, we even don't require this much calculation. So what you can see, this A is equal to what? It is equal to Q2 dot Q0 whole complement. So basically when this will become 0, when Q2 equal to Q0 is equal to 1. So put it like this, 1, 1, and in between put don't care. So when you put don't care, the possible states can be 101 and 110. So if this is the case, basically 101 is what? It is 5, and 110 is 6. So in up counting, you will encounter 5 first. So this state, at this particular state, you will be clearing all the flip flop or resetting the flip flop. That means from 0 to 4 you are counting. So that means mod 5. Within 30 seconds, not even 30, within 15 seconds, you can solve this question and move on to the next question. 101 and 111. What is 11? Oh, yes, sorry. 111. So this will be 7. So out of 5 and 7, 7 you will encounter first in your up counter. So that is why it will be resetted over here. Okay. So next question, tell me now what will be this? So you can see such kind of question has been asked recently also. Just give me a minute. So let me check how many more questions we have. What answer are we getting? A. Okay, so let us check. So you can see over here we are using reset. Okay, we are using reset. So if this is reset, that means this will be down counter. Okay, this will be down counter. Very good. So now basically over here it is given active low asynchronous reset, RD bar. So asynchronous reset will be activated when you have what? When you have 0 for the first time. So let me assume this is A. So A is equal to Q2 dot, and what is this? Q naught complement. So this is actually reset. Okay, we have to reset. So reset means what? In your down counter, we are searching for zeros. Okay, listen very carefully what I am telling. We are searching for zeros to reset them. And over here, this will be reset when both Q2 and Q1, Q0 are, means this will become, A will become 0 when both Q2 and Q0 are 1. So that means Q2, Q1, Q0. So 1, 1, and this is complement. But when we are down counting, remember, when we are, have I done something incorrect? No, this is okay. So when we are down counting, so that means, so either we will have this state or we will have this state. Okay. So why did you guys tell me up counter? This is down counter. So someone said option A. Shubham, why are you saying option A? Reset. Oh, sorry. So reset input. It is actually preset. Very bad. So that is what I was thinking. Why they have taken AND gate? Sorry, NAND gate. I am very sorry. So this is up counters. Why did you guys tell me down counter? Okay. So is this down counter, means you are telling me down? This is up counter. You guys na. So this is up counter. Why will it be down counter? You have reset input. Okay. Reset means it is actually what? Over here it is clear only. Reset means, what do you reset? You reset the 1 to zeros. Okay. Reset means clear input only. This is active low. Same question has been asked, I guess. Yes, the same question. So this is also mod 5 up counter. And Shubham, you have said the wrong thing. This is not down counter. And still you are getting the same, means correct answer. See over here, this is written RD complement. Reset means what? What is reset? Reset means basically Qn plus 1 goes to 0. So wherever you have clear bar, so I can even write this as reset bar. Okay. So now if you see, this A is equal to what? It is equal to Q2 dot Q naught whole complement. So this is actually what? This is your up counter. So in up counter, this will become 0 when Q1, Q naught is both equal to 1. So again, I am going to 1, don't care 1. So this will be either 101 or 111. As this is your up counting, so this state will be encountered first. So from 0 to 4 you will be counting. So mod 5 binary up counter. You can see the exact question has been repeated. In 2002 this was asked, and this is asked in 2015. The exact same question Only thing they have changed is they have written this clear bar as reset input. Did we understand or not? Did we understand? Tell me. What about others? Piyush, Chandana, Raju? Fine. So now solve this question. So there is one important concept over here. B. Okay, we will see. A. So we have two different answers. B, A. See, what is the concept? If suppose we are counting up or down, it doesn't matter. If you are counting up counter, suppose if we have a mod 8 up counter, so counting sequence will be from I should have drawn the diagram a little bit properly. So look over here. So for up counter, so look over here. This is your normal mod 8 up counter. So let us assume this is C. QC means this is QB, this is QA. So we know what? We apply your clock frequency to this. So this over here, you can see, we know what? That we have over here. This is F clock by 2. Frequency get half over here in the MSB. Over here, what will happen? It will be F clock by 4. And at this point, it will be F clock by 8. Now the same thing you can even do for down counter. Okay. But what will happen if suppose this is mod 4 up counter? So mod 4 up counter will count from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and again the next states are going to repeat like this. Okay. So I shouldn't have taken mod 4. So let us assume that it is mod 5. Okay, mod 5. So next will be 1, 0, 0. This is your mod 5 up counter. So let me write it over here. So you can see what? The states are continuously repeated. Okay. So this is the counting state of mod 5 up counter. So if this is your QC, I don't have space over here. So this will be QC, this is B, and this is A. Now look over here. What is the frequency? What is the repetition over here? So you can see it is not repeating like this. Okay, it is not repeating like this because here we have two zeros. So basically it is repeating like from over here to here. Then once again from here you are getting the repeated state. Okay, so here you can see it is repeating after this much state. So basically how many clock cycles are taking place? So this is 1, 2, 3, 4. Sorry. So this is 0th clock pulse, means this is first, second, third, fourth, fifth, sixth. Why am I getting sixth over here? Okay, sorry. So this is the repeated state. So I should have drawn it like, wait a minute. So if I am taking from 0, it should again start repeating from 0. Okay, so this is the repeated state. Okay, so this is one repetition, this is another repetition, this is one more repetition. So this will be f clock by, so 1, 2, 3, 4, 5, f clock by 5. Now look over here for B. So you can see it has 00, 11, again 00. So over here we have 00, 11, then 000, 11, then 000, 11. So that means this is the repeated state. 000, 11. Sorry. So look, from 000, 11, this is one repetition. Then again we are getting 000, 11. So I haven't taken it from here because here we don't have 000. So here you can see it is getting repeated from here 00011, 00011. So this also has frequency f clock by 5. Now look for this MSB term. So over here you can see there are 4 zeros then 1, 4 zeros 1, 4 zeros 1. So this is also getting repeated like this. First 4 0 then 1. Once again you are having 4 zeros and 1, 4 zeros and 1. So all the bits are actually what? It has frequency f clock by 5. So whenever we have mod 5 up or mod 5 down, our frequency, it is same in all the bits. Okay, it is same in all the bits. Now look over here. You can see there is clear input applied, and basically if I assume the output of this clear as x, so x is equal to what? Q3 dot, and this is Q1 whole complement. So this will become 0 when Q3 is equal to Q1 is equal to 1. So right over here Q3, Q2, Q1, Q0, and out of this Q3 and Q1 is 1, remaining is don't care. So this is up counter. So you will be encountering states like this. So this will remain constant. So either it can be 0 0 or 0 1 or 1 0 or 1 1. So in up counting you will encounter the state first. So this is what? This is your, sorry, 10. Okay, this is 10. So this will not be counted. This state, it will not be counted. Your counting state will be from 0 to 9. So that means this is mod 10 up counter. If this is mod 10 up counter, so they have asked basically the frequency over here. So it will be what? It will be f clock by 10 in all the places. Even if they have asked frequency over here, it would have been f clock by 10. Even over here if they had asked, so it would have been f clock by 10. in any of the output, if they had asked, it would have been f clock by 10, but they are asking what will be the output signal of y. So you can see over here, f clock is given as 10 kilohertz. So 10 kilohertz divided by 10, so that comes out to be 1 kilohertz. So option B is your correct answer. So Shubham had given the correct answer. Tell me if this is clear or not. Each one of you tell me if this is clear. Any doubts? So this was a good question. Okay. So now we have is this question. So tell me what will be the answer. So these are the negative edge triggered flip flop. Okay. So whenever you get such kind of question in exam, you need to very quickly redraw this much part. These are the answers. W1, WT, W2, W3, W4. But you need to very quickly draw this part. So okay, I have decided today I will leave you guys after this. So it's okay. We can study the concept of setup time, hold time, and master slave flip flop in the next class. Okay. What happened? It will be very easier for me actually to draw this. So now look over here. Basically, they have given us this diagram. Okay. Now don't think why am I drawing this straight line. Okay, to synchronize all of them at a same point. Okay, so that is why, because I have broken the three parts. So don't worry, later on I will be showing you what I am doing. So look over here. Basically, so let me extend all the clock. So these are negative edge triggered, and you can see in the negative edges only you have to find the transition. So this question, when we had first started the concept of flip flop, it is from that. Only thing is that how many of you are able to recreate this diagram? That's it. So now look, this is what? This is your negative edge triggered flip flop. So x1 is the input to flip flop 1. So these are all the negative edges. This is one negative edge, this is one negative edge, this is another negative edge, and this is negative edge. So your inputs are allowed to make transition only at the negative edges. So now if I draw the diagram for Q, so let me write this as Q1, this is Q1, and this is Q2. So first let me draw Q1. So Q1 if you draw, so this is the clock to Q1 and X1 is the input. Okay, so look very carefully what will happen. So first I am drawing Q1. So Q1 you can see at this negative edge, this is 0. Okay. At the next negative edge, you can see the output has transitioned from 0 to 1. Look over here, it has transitioned from 0 to 1. So that means immediately this is also going to be at 1. So I should use a deep pen over here. So this will stay at 1. Notice the state that we have at the next negative edge. So that is also 1. So this will continue to be at 1. And again at the next negative edge, this is at 1. So it will go on like this. So this is what? This is your Q1. Now let us put X2. Okay, so this is my X2, you can see X2. Now for X2, I have to calculate Q2. So this is also negative edge triggered. So I have to calculate the output Q2. So you can see over here that at the negative edge, this is what over up to this point, it is 0. And in the next negative edge here also it is 0. So it will stay at 0. In the next negative edge over here, this is still at 0. So this will remain at 0. In the next negative edge, this is again 0. Okay. What is happening? So everywhere it is 0 only. Here it is 0. Here also 0. Here also 0. And for the first time it is becoming 1 over here. What is this? Fine. Now you can see what? This is your Q2. So output is what? It is equal to Q1, Q2. So if you multiply this two, so this will be simple like this. Only at this place we are going to have 1. So do we have any such option? So this is your Y. So let us check where is our option. Yes, you can see W3 is that kind of option we are getting. Look, Y and W3, it is both same. So that means W3 is the correct answer for this question. Tell me if this is clear or not. How many of you got W3 as your answer or this waveform? Good question to confuse us. Yes. Now you guys don't need to confuse yourself. See, even if means I had suggested you that you need to draw this, but even if you didn't draw, then also you could have done it. Okay, you could have done it. Now I will show you how. Chalo. If suppose we don't want to draw the diagram, so just see, I am looking in the screen and I will continuously drawing it. Okay, but only thing that you need to do is what? You need to continuously look at your screen. Continuously look at your screen and then draw. So just mark the clock negative edges you need to mark. That's it. So let us assume this is the first negative edge, second negative edge, third negative edge. Cannot take this much space. So first negative edge, second negative edge, third negative edge, fourth negative edge. So how many negative edges we have? 1, 2, 3, 4. So now look over here. How am I drawing? So this X1 is basically what? It is the input of your D1, D flip-flop. So look, initially before the first, so this is what? This is your first negative edge. So over here you have 0. So first I am drawing what? I am drawing your Q1. So this is 0. See, I am just looking in the diagram. Then at the next negative edge, at the second negative edge, so this is your first negative edge. So I should have drawn it like this. This is at the first negative edge. Up till this point I have drawn. Now at the next negative edge, this is going to be 1. Okay. So at the second negative edge, this is going to be 1. So I have drawn it like this. Now look at the third negative edge. It will stay at 1 over here. At the fourth negative edge also, this is going to stay at 1. So this is your Q1. Now look for Q2. So at Q2, you can see what? That this is your first negative edge. Before that, you have 0. So this will be staying at 0. At the second negative edge, again it is at 0. Fine. At the third negative edge, again you have 0. At the fourth negative edge, you have 1 for the first time. Okay, so now multiply this two waveform. You can see this will be 0, 0, 0, particular at this point, you will have 1. So even without drawing the diagram, you could have drawn it like this. Okay, you could have drawn it like this by only marking your negative edges of the clock. So I have marked the negative edges of the clock. Is that clear? Is that clear? Now, if you don't want to take this much risk, you can do what? Simply draw the clock pulse. Then also it's okay. It won't consume that much time. Even if you draw the clock pulse, now it will be far more easier to see. Okay. Is this clear? Tell me, everyone. Is this clear? Okay. So next concept we have is that of setup time and hold time. So it's okay. We will see this in the Sunday session. Okay. So I will bring few more questions over here. So this is one very good important question. Concept of setup time and hold time. So that day, Piyush, you also gave me one question of setup time and hold time. I told you in the next session we are going to discuss. I guess the class before the next previous session. Okay. So it's okay. In the next session, we are going to finish this chapter and we are going to even solve few questions. So I will bring few more questions. Okay. And then we are going to finish this chapter along with, if time gives, means if there is some more time. So we will finish that combinational circuit part also. Okay. So I will end the session over here. If you guys have any doubt, you can ask. And Shubham, those of you who have not seen the recording, please see the recording of all the sessions. Okay. Please see the recording of all the sessions or else it will be little bit difficult. Yeah.